Hello all, welcome back. In the previous lecture we were discussing about the excess rainfall and the corresponding direct runoff. We have seen different methods for estimation of excess rainfall. So, different methods we have seen in the previous lecture are phi index method, infiltration methods, runoff coefficient and also SCS curve number method. We will start with the phi index method. So, example 1 is related to estimation of runoff. So, let me first read out the question. The following table represents the set of observed rainfall data for 70 minutes at an interval of 10 minutes in a watershed. If the value of phi index is 4 centimeters per hour, estimate the total runoff at the outlet of the catchment. So, the rainfall data is tabulated over here, time is given in minutes and rainfall intensity is given in centimeters per hour. So, you need to be very careful, intensity is in centimeters per hour and time is given in minutes. Now, let us solve the problem. Before that, let us revisit into the data given. Rainfall data for 70 minutes at an interval of 10 minutes given to us. Phi index 4 centimeters per hour is also given to us. So, we know if phi index is there, how to compute the runoff depth. Phi index is representing the constant rate of abstraction from a catchment. So, once that data is available to us, corresponding to that how much is the quantity of water which is lost as abstraction can be calculated. Once we deduct that value from the total rainfall data, we will get the corresponding excess rainfall which is equivalent to the direct runoff depth. So, we need to find out the total runoff at the outlet of the catchment. So, with the given data is time and rainfall intensity. So, with that we can draw the rainfall hydrograph. That is already plotted here. Hydrograph is shown over here in this graph and the data which is given to us is 4 centimeter per hour is the value corresponding to abstractions which is given as the phi index value. So, that is tabulated in this column. 4 centimeters per hour can be marked over the graph like this. So, this is a constant rate of abstraction. So, it will be a straight line all throughout the time period. So, you can see 4 centimeter per hour which is representing the phi index value is demarcating the excess rainfall and the abstractions. So, here we can understand that the rainfall which is coming above the phi index value will be contributing to the direct runoff which is marked over here by the dash lines. So, excess rainfall we can calculate. So, you can observe the data. For the first 10 minutes, 0 to 10 minutes, 2 centimeter per hour is our rainfall data, phi index is 4 centimeters per hour. So, the constant rate of abstraction is more than that of the rate of rainfall. So, definitely whatever rainfall is occurring, everything is lost as abstraction. It may be in the form of initial abstraction or it may be in the form of infiltration. So, 2 centimeters per hour is the rainfall intensity and 4 centimeters per hour is the phi index. So, excess rainfall will be 0. And second case, that is from 10 to 20 minutes, we got a rainfall of 5 centimeters per hour and phi index is 4. So, the difference between them will be giving us the excess rainfall corresponding to that time period, that is 1 centimeters per hour. In that way, for the next time period it will be 8 minus 4, that is equivalent to 4 centimeters per hour. For 30 to 40 minutes it will be 7 and 4, 7 minus 4, 3 centimeters per hour. That way we can calculate the excess rainfall depth. So, for all the time intervals we have computed the excess rainfall. Now, the time interval is 10 minutes gap. So, the intensity is given in centimeters per hour and the time interval corresponding to each intensity is 10 minutes. So, both the units of time should be made to same unit. So, corresponding to this excess rainfall centimeters per hour is there with us. So, corresponding to this time interval we need to calculate 1 centimeters per hour for 10 minutes. So, that when we convert it into centimeters we will get 0.17 centimeters, and in the similar way corresponding to all the time intervals we will compute the runoff depth. So, certain time intervals are not contributing towards runoff, those values have been taken as the abstractions, and remaining which is coming above the phi index value is contributing towards the runoff at the outlet. So, we got the runoff depth corresponding to each time interval. So, those values will be added together to get the total runoff at the outlet of the catchment, that is coming out to be 1.84 centimeters. Once the depth of water corresponding to each interval which is going as the abstraction is calculated, that when deducted from the total rainfall will be giving us the runoff depth. So, the total amount of runoff which is calculated is 1.84 centimeter related to this problem. Now, let us move on to the second example. First example was very simple because directly the phi index value is given to you and rainfall hydrograph is given to you. Now, second one is estimation of phi index. In this case definitely you need to be given the runoff depth. So, this phi index method is applicable to gauged catchments. So, from the measured runoff depth value and the rainfall depth value, we will be calculating the phi index or the constant rate of abstractions which may happen from a particular watershed. The following table represents the incremental rainfall for successive 1 hour interval which produces a direct runoff of 6 centimeters. So, the rainfall data is representing corresponding to 1 hour time interval, and the runoff which is produced, direct runoff, is 6 centimeter. The rainfall data is tabulated here in this particular table, time in hours and incremental rainfall depth in centimeters given to you, and runoff depth is 6 centimeter. This rainfall is producing a runoff of 6 centimeter at the outlet of the basin. We need to calculate the phi index value. The data given actual runoff 6 centimeters and total rainfall 14.75 centimeter. From the table which is given to us, total rainfall for the entire time period can be calculated. It is calculated as 14.75 centimeters and the corresponding hydrograph is plotted. Now, what we need to determine? We have been given the runoff depth. We need to calculate the phi index value for this particular storm. So, for this what we will be doing? We need to make certain initial guess related to phi index. So, initially thinking of the initial abstractions and the high value of infiltration in the beginning of the storm, we can assume a certain phi index value between certain time interval. Here what I am going to do, I am going to assume a phi index value between 0.5 and 1 centimeters per hour. So, we are going to assume phi is equal to 0.75 centimeters per hour. So, it can be up to you. If you are a very experienced person, you are having an amount of actual runoff and also rainfall value. From this rainfall value, what should be the abstractions which has to be subtracted to get this much of runoff value? From experience, you will be getting that value. Your initial guess may become correct, but for a beginner, we need to start like this. We have to assume a phi index value. Here I am assuming 0.75 centimeters per hour as the first guess for phi index. So, if phi index is 0.75 centimeters per hour, you can understand that from 0 to 1 hour, that is 1 unit is marked at the center, it represents this time interval is 1 hour. So, during the first hour whatever rainfall is occurring, that is getting infiltrated or it is lost as initial abstractions, and also the last ordinate also, that is corresponding to 7 hours to 8 hours. The rainfall corresponding to that particular time interval is also lost as infiltration or abstraction. So, whatever comes above will be taken as the runoff depth. So, what we will do, corresponding to this assumption, that is phi is equal to 0.75 centimeters per hour, we will calculate the runoff depth. Then we will compare with the actual runoff depth. If both are matching, our initial guess is correct. If it is not matching, then we may have to go for second trial. So, we can start solving the problem. So, estimated runoff corresponding to phi value 0.75 centimeters per hour can be calculated. That is, this ordinate will be going as abstraction corresponding to first hour and last 1 hour. Above that, that is above this phi index value, that is contributing as the runoff depth. So, this is calculated as estimated runoff is coming out to be 9 centimeters. This is similar to that of the previous problem. In the previous problem, phi index value is given to us. Here in this case, we are making an initial guess of phi index value between 0.5 and 1, or it can be assumed between 1 and 1.5 also. Based on your assumption and with the calculated estimated value of runoff depth, you can change the initial guess value. So, here in this case, with the phi index value 0.75 centimeters per hour, our estimated runoff value is 9 centimeters. So, this estimated value of 9 centimeter is more than that of the actual runoff. Actual runoff is given out to be 6 centimeters and estimated is 9 centimeter. So, we can understand that with the assumed phi index value, that is the constant rate of abstraction, which is assumed as 0.75 centimeters per hour, is producing a runoff depth of 9 centimeters, which is more than that of the actual runoff. So, the abstractions which is taking place is less. So, that value need to be increased than that of the initial guess. Therefore, phi should be greater than 0.75 centimeters per hour. So, in the next guess, what we will be doing, same figure, we are going to assume a phi index value of 1.25 centimeter per hour. From where this 1.25 is coming, initial guess was between 1 and 0.5, and second guess we are going to make between 1 and 1.5. That interval rainfall intensity for which the phi index value will be constant, which gives the actual runoff depth, that we need to determine. So, initial guess was giving us an overestimated value of runoff, which was more than that of the actual runoff. So, what we need to do? We need to increase the constant rate of abstraction. That is why we have increased the phi index value from 0.75 centimeters per hour to 1.25 centimeters per hour. Now, we will repeat the computation in the similar way as we have done previously. So, estimated runoff will be coming out to be 6.25 centimeters. So, here also you can see actual runoff is 6 centimeters and our estimated value is more than that of the actual runoff. So, phi index should be greater than 1.25 centimeters per hour, because the abstraction should be more, then only the runoff calculated will be less, because we need to reduce the computed runoff value, then only it will be matching with the actual runoff depth. So, in the third trial, we will assume a phi index value of 1.5 centimeters per hour. So, trial 3, our assumption is phi is equal to 1.5 centimeters per hour. So, estimated runoff will be around 5 centimeters. So, here you can understand that when the constant value of abstractions came out to be 1.5 centimeters per hour, or the phi index value of 1.5 centimeters per hour produced a runoff depth of 5 centimeters, that is less than that of the actual runoff depth which is occurring there at the outlet of the watershed. So, what we have to do? We have to reduce the phi index value, right. In the previous two assumptions, previous two guesses which we have made, estimated runoff depth was calculated to be more than that of the actual runoff depth. Here in the third trial, it is found out that it is less than that of the actual runoff depth. So, abstractions should be reduced. For a value corresponding to phi is equal to 1.25 centimeters per hour, we got an overestimated value of runoff depth. And in the case of phi index value, phi is equal to 1.5 centimeters per hour, it was an underestimated value. That is, the value of phi should be between 1.25 and 1.5 centimeters per hour. And this much of water will be lost as abstractions. And beyond what is coming, that is producing the direct runoff. That value we need to quantify. So, we know if this is phi, this red line is representing phi, and that is corresponding to how many hours. So, we can easily understand that from time 0 to 2 hours, entire rainfall is lost as abstractions, and also from 7 to 8 hours also the rainfall is lost as abstraction. But in between 2 hours to 7 hours, that is from here to here, we are having constant rate of abstraction represented by phi index value. So, once we deduct that abstractions in terms of phi value from the total rainfall, we should get the runoff depth. So, that is what I am writing over here. 14.75 centimeters is our total rainfall. Total rainfall minus total abstractions will be giving you a runoff depth of 6 centimeters. So, how these abstractions are calculated? For 0 to 1 hour, it is 0.5 centimeter, 1 to 2 hours, it is 1 centimeter, and 7 to 8 hours, it is 0.75 centimeters. And in between from 2 to 7 hours, we are having a constant abstraction of value equal to phi. So, for that we can compute the quantity by multiplying the phi index with the corresponding time interval. So, how many hours are there in between 2 to 7? It is 5 hours, and a constant rate of abstraction is 5 centimeters per hour. So, phi multiplied by phi plus abstractions corresponding to other time intervals together will be the total abstraction. That abstraction subtracted from the total rainfall will be giving you the direct runoff depth, that is 6 centimeters. So, by making use of this formula, you can calculate phi index value as 1.3 centimeters per hour, or you can proceed in the way as we were making the initial guesses. So, that way next trial you can go ahead, but how many trials you may have to proceed, we do not know. But here one thing is certain, that our phi index value is between 1.5 and 1.25. So, we got how much should be the abstractions. So, we are assuming phi as the phi index value, and we know the time intervals corresponding to that constant rate of abstraction and corresponding to the abstraction value less than phi index value. So, total abstractions we will calculate in terms of phi index, and that we will deduct from the total rainfall value, which will be equated with the total runoff depth at the outlet of the watershed. So, that way we can determine the phi index value. So, in these type of problems, you need to have runoff depth or phi index given to you. So, these type of approaches are applicable to gauged catchments. Now, third method was related to runoff coefficient. Runoff coefficient is, we know how to calculate, the formula is given. So, I am not working out separate problem related to that. Let us directly move on to the numerical example related to infiltration equations. So, here what we are going to do, how those equations can be utilized for finding out the abstractions, and after that deducting those abstractions from the rainfall depth to calculate the direct runoff depth. So, these type of methods, that is computing abstractions by making use of infiltration equations, assumes that all the abstractions are taking place due to infiltration only. All other abstractions are neglected. and by making use of the infiltration equations, we will calculate the total volume of water getting infiltrated, that we will be deducting from the total rainfall depth to get the excess rainfall. Any of the equations can be utilized if the data is available. Here we are going to deal with the Horton's equation. So, let me read out the question. A catchment experiences a rainfall of 4 centimeter, 5 centimeters and 3 centimeters in 3 consecutive hours. The infiltration rate equation for the catchment is given by the following equation, that is f of t is equal to 1.2 plus 4.2 e to the power of minus 2.5 t. Estimate the surface runoff from the basin assuming all other losses to be negligible. So, here you can see infiltration rate is represented by means of an equation. That equation is given to you, and runoff rainfall depth is also given to you for continuous consecutive 3 hours. Rainfall in terms of depth is given to you, that is hydrograph is given to you, and the infiltration rate equation is also given to you. And once the quantity of water corresponding to that much of infiltration is quantified, that value can be deducted from the total rainfall value to get the excess rainfall, which is equivalent to the direct runoff. So, let us revisit into the data given. This is our rainfall hydrograph which is given to us. So, this one is representing from 0 to 1 hour, 1 to 2 hours and 2 to 3 hours. So, with that interval, how much is the rainfall occurred, that is what is shown over here. This is our rainfall hydrograph. Total rainfall you can calculate 4 centimeters, 5 centimeters and 3 centimeters. So, this is coming out to be 12 centimeters. Now, infiltration equation is given to you in the form of Horton's equation. You might be remembering Horton's equation which we have covered in 3rd module. F of t is equal to f of c plus f naught minus f c e to the power of minus k t. This is the form of Horton's equation. So, the given equation is similar to that of this equation. You can compare each other. So, here we can take f c, that is the constant rate of infiltration, equal to 1.2. After comparing these two equations, we can understand that f of c is 1.2 centimeters per hour. Now, this 4.2 is representing the value corresponding to f naught minus f c. F naught minus f c is 4.2, f c is 1.2. So, we can get the value corresponding to f naught. Or one more way to calculate f naught is that when time t is equal to 0, how much will be the infiltration? That is the value corresponding to f naught. Initial infiltration is represented by f naught. So, we can calculate f of 0, t is equal to 0, we are substituting, we can calculate f naught as 5.4 centimeters per hour. F of t can be written as f c plus f naught minus f c e to the power of minus 2.5 t. F c is 1.2, f naught is 5.4. So, this is our Horton's equation. Now, that we can plot over here. When we plot this, the curve will be looking like this. Infiltration curve represented by Horton's equation. By making use of the values which is given by this equation, we have utilized to plot this curve. So, now you can see up to a certain point, that point is corresponding to the meeting point of the infiltration curve and the rainfall hydrograph. So, when we were discussing about the potential infiltration and actual infiltration, we have seen that if f value is greater than intensity of rainfall, all the water which is falling as rainfall will be infiltrated into the ground, right. So, here you can look at the curve, infiltration curve and the rainfall hydrograph. Up to a certain time, rainfall intensity is less than that of the rate of infiltration. So, till that time, whatever rainfall is falling on the ground will be infiltrated into the ground. After that particular time, here which is marked by this yellow dot, you can see that infiltration is drastically reduced and rainfall which is experienced by the catchment is more than that of the infiltration rate. So, first we need to understand, or first we need to calculate the value of time corresponding to this meeting point of the infiltration curve and the rainfall intensity hydrograph. That is, corresponding to that time, whatever rainfall is occurring, that is converted to abstractions. So, that can be denoted by the time TR. So, this we need to determine now. So, for T less than TR, when time T is less than TR, infiltration rate is equal to I, F is equal to I, that is F is equal to 4 centimeters per hour. Now, we can determine TR, that is we are going to make use of the equation, infiltration rate equation. We know the infiltration rate corresponding to the value of time T is equal to TR. So, 1.2 plus 4.2 e to the power of minus 2.5 TR is equal to 4. From this we can calculate the value corresponding to TR. TR can be calculated as 0.162 hours. So, that we can understand, initially it is starting from 0 to 1. So, it is less than 1 hour, it is calculated to be 0.162 hours. At 0.162 hours or before T is equal to T less than 0.162 hours, whatever rainfall is occurring, it is lost as abstractions. When T is more than this 0.162 hours, whatever rainfall is coming, from that the infiltration we are deducting, we will get the excess rainfall. So, up to T is equal to TR, that is equal to 0.162 hours, there will not be any direct runoff. So, that I am showing by means of hashed areas. So, this much is the, that is up to T is equal to TR, whatever rainfall is occurring, that has been lost as abstractions. And now, the area which is coming under the infiltration rate curve, that will be contributing towards the subsurface flow, that is infiltrated into the ground, remaining water only contributing towards the surface runoffs, that we need to quantify now. So, for T greater than TR, that is T greater than 0.162 hours, our runoff will be starting. So, we need to quantify the rainfall value after 0.162 hours, which is contributing towards the runoff value. So, the runoff will be starting after this T is equal to TR. So, that portion of the rainfall data, rainfall hydrograph, which is marked by means of these green hatched lines, is representing our excess rainfall or the direct runoff. So, how can we get the volume of water corresponding to direct runoff? Now, we know that we have demarcated the region between the abstractions and the excess rainfall. Now, what we have to do? We have to quantify the total amount of water which is infiltrated. That can be deducted from the total rainfall, which will be representing our direct runoff. So, we need to quantify the total volume of water or total depth of water which is infiltrated. So, that is nothing but our cumulative infiltration. So, total infiltration is represented by capital F of T. So, we know corresponding to TR, the rainfall intensity is 4 centimeters per hour. So, we can understand that this much area, that is 4 into 0.162, is completely lost as abstraction, and from time T is equal to 0.162 to 3 hours, that is till the end of rainfall, cumulative infiltration can be calculated by integrating the infiltration rate. That is what we are doing. Before T is equal to, that is for the time T less than TR, entire rainfall is infiltrated. So, ITR will be considered as the cumulative infiltration up to the time of ponding. So, that time after T greater than TR, whatever is coming, from that we need to calculate the cumulative infiltration, and both should be summed up to get the total infiltration, that we will be deducting from the total rainfall value. So, time durations we are dividing into two parts, that is 0 to TR and TR to till the end of the rainfall. That is TR is 0.162, 0 to 0.162, whatever intensity of rainfall is there, entire value is converted to infiltration. So, that total value of infiltration up to time t is equal to 0.162 can be calculated by using 4 into 0 ITR. I into TR will be giving you the cumulative infiltration up to t is equal to TR. After t is equal to TR till the end of the rainfall, from time t is equal to TR to the end of the rainfall, we can calculate the cumulative infiltration by integrating the infiltration rate equation, that is small f of t can be integrated between that time duration, which will be giving us the cumulative infiltration corresponding to time between TR to Tmax. So, that is what is written over here, that is integral 0.162 to 3, 1.2 plus 4.2 e to the power of minus 2.5 t dt. So, when we integrate that and after that if we sum up, we will get the infiltration water to be 5.2 centimeters. This you can work out and see whether you are getting it as 5.2 centimeters. So, the total depth of infiltrated water is calculated to be 5.2 centimeters. And direct runoff is total rainfall minus cumulative infiltration. That is total rainfall for that period how much it is minus cumulative infiltration for that time period, that will be giving you the direct runoff depth. So, total rainfall we know 12 centimeters and cumulative infiltration we have calculated 5.2 centimeter. So, 12 minus 5.2 will be giving you the direct runoff depth, that is 6.8 centimeters. So, by making use of infiltration equations, whether it is Horton's equation or Greenamt equation or Phillips equation, if the parameters corresponding to those equations are available to you, you can calculate the cumulative infiltration how much it is coming. So, that cumulative infiltration if you are deducting from the total runoff value, you will get the direct runoff. But here you need to understand at what time the ponding is occurring. That detailed explanation we have seen with the help of Greenamt equation, time to ponding, and after ponding how much infiltration can be occurred, that also we have seen the equation by using Greenamt equation. In the similar way, here also we need to find out at what time the time corresponding to infiltration rate equal to intensity of rainfall, that we need to determine. Till that time entire water is infiltrated into the ground, after that water will be contributed towards runoff. So, that way we need to calculate the cumulative infiltration, and after getting the cumulative infiltration value, that we will be deducting from the total rainfall value to get the runoff depth. Now, let us move on to the fourth example. It is related to estimation of surface runoff using SCS method, that is our SCS curve number method. So, the question is, a catchment has 40% type B soil and 60% type C soil. The land cover is 50% good condition, half wooded and half residential. Assuming a normal moisture conditions, determine the direct runoff from a storm of 150 millimeter from this catchment, assuming the growing season. When we were discussing about SCS method, SCS curve number method, we have seen the moisture content is related to antecedent moisture content when we were explaining. Corresponding rainfall values have been given in a table. The growing period and also dormant period, dormant condition and also growing stage is given in that. So, here in this problem it is related to growing season. Corresponding to that, the value should be taken from the table. So, the catchment description is there. In this catchment we are having 40% of type B soil and 60% type C soil. Different types of soil is present in the catchment. So, depending on the soil characteristics, SCS has provided 4 groups A, B, C, D. Out of those 4 groups, in this catchment type B soil and type C soil is present, and it is given that 40% of the area is having type B soil and 60% type C soil. The land cover is also given because the curve number value is dependent on the soil property and the type of soil and also land use properties. So, land cover details are given as 50% of good condition, half wooded and half residential. So, 50% land is there, out of that 25 is wooded and 25 is residential. So, 2 areas, we can divide the entire catchment into 2 areas, 50%, 50%, and in each area we are having half of wooded in good condition and half residential. So, based on these land use classification, we need to take the curve number from the table which is given in the textbook, and this is based on normal moisture condition, that is AMC 2, antecedent moisture condition 2 is considered here. And if it is something related to dry and wet, dry season, dry condition and the saturated condition, we have to go for AMC 1 and AMC 3. So, it is given that normal condition, so we need to go with the AMC 2 condition. So, let us find out the curve number for this particular land use. So, land use is given, we can find out the curve number first. So, given land use is wooded and residential area. Wooded area is there and residential area. Soil group in both these land use conditions, we are having soil group B and soil group C. So, that way we are having soil group B and C in both the land use condition. Wooded condition also soil group B and C present, residential area also soil group B and C are present. Now, percentage of this area, it is already given 50% of good condition, half wooded, half residential. So, initially the catchment is 40% type B and 60% type C. So, type B soil is 40% and type C is 60%. So, that condition we will apply to both wooded land use and also residential area. So, we need to find out the percentage of area. So, the entire area is divided into 50%, that is 0.5 of 40% type B soil and 0.5 of 60% type C soil in wooded land use. In the similar way, corresponding percentages for residential area also, that we have calculated, it is found out to be 0.2, 0.3 and 0.2 and 0.3 for residential area also. Now, we can compute the curve number corresponding to wooded area. Curve number corresponding to wooded area I have taken from Singh 1992 textbook. So, for wooded area for type B soil it is 55, wooded area type C soil it is 70, and residential area soil group B it is 75 and residential area soil group C it is 83. So, these tables are available to you in any of the hydrology textbooks which is covering SCS method. Majority of the basic textbooks are covering SCS method for estimating direct runoff. From that textbook you can take the values corresponding to curve number. But now the issue is that not a single value of curve number is representing the catchment. We are having 4 different groups, 2 types of soil and 2 types of land use areas. Based on that, we are having different percentage of land areas which is having different curve number value. So, we need to calculate the weighted curve number value. So, weighted curve number value can be calculated as 0.2 multiplied by 55, 0.3 multiplied by 70, 0.2 multiplied by 75, 0.3 multiplied by 83. All will be summed up to get the weighted curve number. It is coming out to be 71.9. So, from the value of 71.9, you can understand it is a natural area. If the area is a water body or a completely paved impervious area, CN value will be 100. For any other areas, the value will be between 0 and 100. So, here the weighted curve number value is calculated to be 71.9. So, once curve number value is known to you, curve number value is available to you, you can calculate the potential retention represented by S. So, we can calculate potential retention S given by this formula. Here we will get S in terms of millimeters, because we have already made use of the multiplying factor, that is the inch conversion to centimeters, and that is again converted to millimeters. That is why it is having 25,400 and 254. If it is in centimeters, it will be 2,540 and 25.4. So, and if it is in inches, this factor will not be coming, it will be 1010. So, you need to be very careful about the units. So, here all the units are in SI units, so you can convert it into millimeters or centimeters. Here we are going to substitute the curve number value, CN is equal to 71.9. So, you can calculate the potential retention as 99.27 millimeters. S is calculated to be 99.27 millimeters. So, now you can calculate the excess rainfall or the direct runoff by using the formula given by SCS curve number technique. This is the formula for calculating excess rainfall or direct runoff. This we have seen in the previous lecture, how we have reached at this particular form of the equation. So, here what we have to do, we have to just substitute corresponding to the value of potential retention S. So, once we substitute, we can calculate the excess rainfall which is equivalent to direct runoff as 73.66 millimeters. So, the runoff at the outlet of this watershed, which is consisting of wooded and the residential area, and which also includes different soil groups B and C, we can get the runoff value corresponding to that particular catchment as 73.66 centimeters. So, here all the methods I have explained related to excess rainfall or direct runoff computation. First two examples were related to gauge catchments, and third and fourth examples can be utilized for ungauged catchments. So, in the gauge catchments we can make use of any of the techniques, but in the ungauged catchments there are limitations in using phi index value, because for determination of phi index value we need to have the value corresponding to the runoff depth. Based on that only we can calculate the phi index value, that is the constant rate of abstraction from the rainfall. So, if the direct runoff depth is available to you, you can calculate the phi index value, and based on that phi index value you can compute the excess rainfall. And other two problems were related to infiltration equation and also SCS curve number method. So, please try to solve more problems, numerical examples related to this, and here I am winding up this topic. Reference related to this SCS method, that is the curve number, all these things are taken from the textbook of Professor V.P. Singh, Elementary Hydrology. Any of the textbooks related to hydrology will be containing this table. So, different soil group details, all those things, when the topic of SCS is explained, along with that those tables also given. So, here I am winding up this lecture. Thank you.